Thank you very much, Maria, for a very kind introduction, and thank you for the invite. I'm from Technical University of Munich, and I will talk today about some magnetic insulators. Before going further in my talk, I would like to first thank everyone for contributing to the work, especially my group, Christian Bach, and Maxime Mostovoy and Maria Azhar, who is also the chair of this session, for developing the theory for understanding of our results. So, as we know, the technology is evolving rapidly because of high demand of fast memory and communication devices, as well as more storage. So even in last 50 plus years, you can see there are a lot of discoveries. So we are going more and more towards spin currents and new solutions away from charged electronics. My point here is that most of these discoveries are mainly where the information carrier are metallic ferromagnets. Where can we see magnetic insulators? So whether and how we can use them. When we want to talk about magnetic insulator, there is no way you can skip yttrium iron garnet. It is the holy grail, the best magnetic insulator with extremely low magnetic damping. So if you excite the magnetization, it can precess longer before it will align along the applied field, and the magnetic information can travel up to several micrometers within the material. But important point here is if you look the static magnetization, all the magnetic moment below TC in a finite large enough field align along the applied field, and when you rotate the magnetic field, they follow nicely. This is a collinear magnet, but now when we want to talk about non-collinear magnets or some complicated magnets, copper oxacillinate, where copper is the magnetic atom, is an important one. It is not as good in damping, but in quite a competition. It has 10 to power minus 4 at 5 Kelvin. But importantly, if you look, its static magnetization is really rich. So at large enough magnetic fields, it behaves very much like yttrium iron garnet. But when you reduce the magnetic field, the magnetization makes some non-collinear orientation. It's about static magnetization. There is nothing dynamics here at the moment. So you can see some tilts, and these tilts become complicated skyrmions. There was a beautiful talks about it. And the phase diagram is like this. So it's around 60 Kelvin magnet. At large fields, you have collinear magnetism, and at low fields, you have multiple phases. And there are many materials, and there are a lot of types of these textures, a lot of tails, and different reasons. I will not go into all these, but for me, a simple picture in real system is collinear, spiral, or tilt. And this you cannot see because of the color contrast, but it's a knot, and knot is skyrmion. So for example, in these two phases, you can easily use a straightener and remove the curls. However, knot will not go away easily. So that's where your skyrmion is. So just keep in mind this different twist. I will go further. And my question is how I can tell in my magnetic insulator where and which tilt I have. Because we are very good in sending current and measuring resistances. But now we are talking about a magnetic insulator. How we can do that? This is where my story began with spin Hall magnetoresistance. I will show results mainly about the material copper oxacillinate, and then at the end a comparison with another material. The story with spin Hall magnetoresistance is not very old. It's 10 years ago when Matthias Weiler from Walter Meissner Institute detected it accidentally. So they were studying some other experiments with using platinum on yttrium iron garnet, and they saw such effect, but at that time they couldn't understand the reason behind it, and they related it the proximity effect in platinum, so they thought maybe platinum is getting magnetized. And later on, Chen gave the theory, and then there was Nakayama and Ninke-Valistra from Bhatt-Van-Wees group simultaneously provided the experimental evidence for these effects. Later on, many experiments, but what we are going to talk today is about, firstly, how does it work? If you take a heavy metal like platinum with large spin orbit coupling, you send a charge current, you get a spin-dependent scattering, and you will create a spin accumulation at the edges. When it's in close proximity to magnetic insulator, this spin current, which you see here, or spin accumulation, can either be absorbed or reflected back due to spin torque effect. So if it's perpendicular, the spin polarization to the magnetization direction of your insulator, so charge current cannot go through. It's only the interaction between spin accumulation at the interface and magnetization. So large spin torque effect, large dissipation, large resistance. Oh, that sounds really fantastic. Why? Because that means with this theory, which looks simple and very nice, you can understand it. So if your magnetization is fully aligned along y direction, which is the situation here, this term will be 0, and when it's along x-axis, your my is 0, so you will have large effect in this SMR. So far so good. We have angle dependence, meaning if I rotate the magnetic field, my magnetization will follow, and I can understand it nicely. So very happy about it. Let's see. Experiment looks simple. So I have magnetic insulator, I put a Hall bar. By sending current, I can measure the voltage as well as you can say resistance in the transverse direction, just like planar Hall geometry, or longitudinal to the current direction. Theory will give you exactly same results. So you should get exactly same results, only the angle dependence will be shifted if you measure transverse compared to the longitudinal. But effect is the same. Now we want to have a non-collinear magnet, a rich one with different magnetic phases, copper oxacillinate, and let's take a cut at 5 Kelvin. So we will do first experiments here. This is a collinear configuration, and when you decrease the field, magnetization starts to tilt away. And then this angle starts to increase, making a cone, and at some point the angle is almost 90 degrees, and this material will split into 3 phases, multi-domain helical phase. Very important point here that this effect is not dependent on magnetic field. It actually dependent on magnetization and spin accumulation angle. So the angle here for non-collinear phases, the important one is this tilt angle where magnetization is not aligned along the field with respect to the charge current. So what is important is alpha minus phi here. So your equation will look like this. So now you have alpha minus phi. This is beautiful because meaning when I have some twist, I expect to have that my angle dependence will be shifted compared to your collinear phases. And now what about amplitude? Amplitude should also have something. So Maxime Mostovoy actually took the magnetization of the collinear phase. So it's a simple magnetization configuration. What happens is when you reduce the field, this angle starts to open up until it becomes 90. So it's really field dependent texture. So you get amplitude which can be just a field dependent equation. This equation is beautiful. What it tells you, when you are in the collinear phase, when H is equal to Hc2, you are here. You expect to have twice large spin Hall magnetoresistance amplitude than compared to this tilted phase when the angle is almost 90. Okay, we can absorb this. So let's just focus on two phases. You have collinear and you have some tilt. Good. So we did experiments. We had a bulk crystal. We polished it, and then we did a Hall bar and did the experiments. Here is the results. These are the amplitudes obtained from the angle dependence, and you can clearly see that here my signal in the collinear phase is almost the same as the non-collinear phase. So they are almost equal, although I was expecting signal from here to here, and now they are just here in both phases. So you think, okay, twice a difference, who cares? But that's not true, because this simply means that in collinear phase you are increasing the magnetization density, because this effect is sensitive to in-plane moment density. And you cannot increase the moment density compared to the collinear phase. There must be something off, but we have short lifetime. So we proceed with publication. Good.
Sorry,
yes?
sorry. I maybe lost the point, but like, what is on y-axis here?
So it's the amplitude by fitting angle dependence you get. So it's basically A, but denoted here differently.
Okay, sorry, that's why I was.
Thank you for your question. Yeah. And this A, which is experimentally determined, has has discrepancy compared to the theory. Okay, but we proceed. Let's look the angle dependence. So angle dependence is interesting. So you do expect, this is experimental data again. So this is the shift which you get from the angle dependence. So angle dependence looks interesting because you do expect zero tilt away from the field, so it is how it is, so that's nice. And when you go to low fields, you expect the angle will be almost 90. So it agrees qualitatively quite well, although it looks like a jump. We were happy about it. So let's proceed further, but the problem started when we did the temperature dependence. Now we did all these measurements, angle dependencies, fitted the data, get a phase, and then plotted it as function of temperature. What you see here, this color map is all experimental data. So here you see magnetic field, here you see temperature, and the color contrast is your data which shows collinear phase should be no phase between the field and the magnetization. So you see blue, and the phase will increase as you go into the tilted phases. And these dots are from another experiment, ferromagnetic resonance. What is beautiful is that both techniques agree well with the phase boundaries. There are some ifs and buts, but okay. We were happy. This is nice. It shows that you are very sensitive to different magnetic phases of copper oxacillinate. But the problem started when we look to the amplitude A from the fitting the angle dependencies, which is plotted here. This is the amplitude of the SMR signal versus magnetic field at different temperatures. Let's look the simple curve, easy one. Here what you see that your signal is much larger than collinear phase. This is not what we expected. We expected other way around. Before we were even worried about twice discrepancy, and now your signal is 10 times almost larger in the non-collinear phase compared to your collinear phase. This is where we think something is really off in theory and our experiments. So then what can it be? Could it be that this theory missed some other important term? And actually Maria did a lot of calculations and really detailed analysis. And there we found that there can be another term which is symmetry-wise allowed. And what this term tells that because it's a texture, not only in-plane magnetic density is varying, but also in the z direction there is some projection of magnetization. So this term actually takes into account. And now you see what is this amplitude of this term is increasing in the non-collinear phases and almost zero in the collinear phase. So combining these two effects at low temperature fits our data very well, because now we have this additional signal which we wanted to have. Now our experiment explains well, good. There is a detailed analysis about different phases and how well we can now establish understand our data for the phase dependence as function of temperature as well as amplitude dependence. So now I would like to tell you about a second material, so which is very different from the copper oxacillinate. It is cobalt chromate. This material, the magnetization as function of temperature looks like this. And here you have multiple two transitions which are spiral transitions, and at one kink you have spiral transition, other kink is also spiral transition here, but it's just the period of spiral changing. That's why I didn't label separately, but you have two actually two transitions which you can identify from magnetization as function of temperature. We had thin film of it, we made the Hall bar, and then we can actually measure the SMR in this sample. Here you can see this is the only amplitude fitting from the angle dependencies. Measurement technique is exactly same. The difference between upper graph and the lower graph is upper configuration is transverse, planar Hall geometry, and lower is longitudinal. You are measuring the resistance along the current direction. But if I see like this, I can clearly see the difference. There is a huge signal at low temperatures for the upper configuration, but not that huge compared to this in the lower configuration. So what it tells you that there must be some difference. So if we compare the previous theory we had for copper oxacillinate, it looks like both contributions are not equally coming into the transverse and longitudinal geometries. Perhaps this B contribution is directional and only appear in some certain directions. This is where I have been through a paper from Jonathan Kipp, which tells that also cites our work and tells about that if you take the conductivity matrix, you can get higher contributions, but some contributions can be directional and chiral. And that can explain this result, but we don't know. This is work in progress. With this short question, I will look forward to your opinion, and I bring you to the summary slides. So we can detect very nicely, and we have a theory for copper oxacillinate which agrees well qualitatively and quantitatively. Thank you very much, and I look forward to questions.